Okay, I'm going to talk to you about how buffers work in this video. This is more going to be just a description, and then we'll do some calculations with it in the next video. So, a buffer is a substance that contains a weak acid or a weak base, and the conjugate ion associated with that acid and base. And the point of a buffer is that it is able to resist changes to pH. So if you add an acid or a base, as long as you don't add too much of it, the buffer will neutralize it regardless of which it is. So here's an example of a buffering system. We could have NH3 and NH4 and then C. I just put Cl because we have to put something there, so any conjugate of anything strong. So NH3 and NH4 plus are the important parts of this buffer. So we can imagine we have NH3 floating around and we have NH4 plus floating around. And they're actually going to exist in some sort of equilibrium with each other. So let's write that equilibrium over here. NH3 and NH4 plus H2O. And this buffering system would naturally be basic because NH3 is a weak base. Now imagine then if we add an acid or a base to this, a strong acid or a strong base, and let's look at what happens. Let's say we add HCl. That's going to react to form NH4 plus Cl, or NH4 and Cl minus. Now, the Cl minus doesn't matter. That's the conjugate of HCl. That's a strong acid, so it's not going to participate in any of this stuff. But the NH4 plus and the NH3 that get created here are going to participate. So this is going to react away this strong acid. So I added a strong acid, and this destroyed it. And now we're going to look at what the buffer does in that situation. So in this situation, we would have removed some of the NH3 and added NH4 plus. What that means then is, according to Le Chatelier's principle, the equilibrium will react to undo the change. So what's going to happen here is this system is going to get driven backwards, re-equalizing these populations back to closer at least to their original values. What that means then is the HCl that was just introduced got reacted away, and the disturbance to the equilibrium was a minor disturbance at best, because there was some sort of disturbance, but then the equilibrium would shift back to counteract it, and as a result there'd be very little disturbance. Let's imagine we added the base NaOH to this system. NaOH would not react with the base NH3, but instead would react with the conjugate salt, or conjugate ion. The Na plus, and then it'd produce NH3, and it'd produce H2O. Again, the NaOH has gone reacted away. It shifted the equilibrium, but it hasn't allowed the pH to swing because it destroyed the strong species. In the meantime, this would cause the NH3 population and the NH4 population to shift accordingly, and this time the equilibrium would try to resist that by destroying the new population and reproducing the population that was disturbed. And so again, the change to the actual buffer would be really minor because the equilibrium would then work to undo the change that adding the NaOH had done. The important thing is, because it has the weak base species and the conjugate weak acid species, it's able to react regardless of whether an acid or a base is placed into. It's able to react regardless to if an acid or a base is produced in the solution. It's able to react away strong acids and strong bases and only leave a weak acid-base equilibrium that still is going to remain fairly undisturbed according to Le Chatelier's principle. Let's say the same thing with a HF-NaF buffer. So here again it's the HF and the F minus that are the important aspects of this buffer. The Na there is just there to give it something to act as the cation, but it's the conjugate of sodium hydroxide, a strong base, so it's not really going to participate in these kinds of reactions. So, available to react is HF and F minus, and before anything is added, the equilibrium that would be set up in the substance is an equilibrium that is slightly acidic. So that's our equilibrium. Now if we want to add, say, a strong acid, it's not going to react with the acid HF, it's going to react with F minus, let's say I add something like HCl. And what that means then is it's going to react to produce HF and Cl minus. And again, the strong acid species will be reacted away, so it is unavailable to cause large pH changes. The increase in the HF population and the decrease in the F minus population, according to Le Chatelier's principle, will be slightly counteracted by the equilibrium trying to shift back, and the overall change from having added the HCl will be very minor in comparison to what you would have expected if you had added HCl to regular water. This buffer also needs to be able to avoid strong changes in pH that are associated with a strong base being added. So let's add NaOH and see how that works out. In this case, we're going to produce H2O, Na+, and F-. And again, the strong base species has been reacted away without the production of any hydroxide, and so the pH hasn't been allowed to shift here. The acid-base reaction has neutralized that new introduced strong species. The corresponding equilibrium will undergo a shift, and that shift will be resisted, and the overall change to the system will be pretty minor. But in the end, by having both a weak acid and a conjugate weak base, the system is ready to react to either acids or bases being placed in, take what would have been large shifts in the hydroxide and hydronium population, and instead reduce them to very minor shifts that can be ignored. So that's what buffers do. They keep the pH of systems relatively stable by providing a weak acid and its conjugate, or a weak base and its conjugate, to react with any strong acids or bases that may enter the system.